Hi everyone, this is the makeup lecture for experiment 3 since we're not having class on Memorial Day. So this week we're going to be shifting to our next class of reaction, which are oxidation reduction reactions, which for short we call redox. So the re for reduction, and the RED for reduction, and the ox for oxidation. So this is going to be our second class of reaction. So we're going to, just like the last class, have to define what is oxidation and what is reduction. Although before we can do that, we have to talk a little bit about some electron bookkeeping, because as we'll see, oxidation reduction reactions are ones in which electrons are transferred as we go from reactants to products. So now for some issues with regards to electron counting. And one of these I already mentioned last week, which was formal charge, and I said I would come back to that this week to explain what that actually is. So formal charge, we saw how to calculate it last week, but formal charge is actually the charge on an atom in a molecule if we take an electron pair bond, right? So in this case, that would be a covalent bond, and just a two electron bond, let's put it generally, and we break that bond in a hypothetical way that we call homolytically. And in this case, if the bond has two electrons, we put each of those electrons onto each atom. So two electrons in a bond, one goes to one atom, one goes to another atom, right? And now this is, as the name implies, this is a formalism, right? We're doing this hypothetically, taking that bond and splitting the electrons evenly. Now, this assumes that the sharing of the electrons is equal in that bond. And therefore, this would be basically an entirely covalent bond. Because here we say, okay, there's no difference of pull on the electrons, so each atom ends up getting one electron when we split that bond in half. Now, the other side of that is something called oxidation number or oxidation state. And instead of taking the bond and splitting it in half evenly, we take that same bond and hypothetically split it in a way that transfers the electrons from the bond to one of the atoms. And in this case, that atom is generally the more electronegative element, because that element has more pull on the electron. So the more electronegative element pulls the electrons towards it because of that electronegativity. Now, in this case, this would be an ionic type bond, because there we actually have a transfer of electrons. Instead of splitting the electrons in half, we are taking those two electrons and putting them onto one of the atoms in the bond. Now, as we can see, formal charge is assuming that bonding is covalent. Oxidation numbers or oxidation states are viewing it as ionic. Now, it turns out that both of these basically electron bookkeeping options are purely formalisms. They are not real charge. They are formal assignments based on electron bookkeeping. And neither is actually accurate, because the real charge on an atom in a molecule is going to be somewhere in between the two of them. So that's important to keep in mind, that whether we look at formal charge or oxidation number, neither of those values we get there are actually the real charge. Getting the real charge on an atom is much more complicated and not something that we can very easily do, given what we would need to solve in order to figure that out. Now, again, we saw formal charge last week when we looked at Lewis structures, or at least started to look at it with Lewis structures. And this week we're going to focus on oxidation number, because oxidation number is going to be incredibly relevant for these oxidation reduction type reactions. Now, unlike formal charge, which is a pretty simple formula where we have to figure out three values and subtract them from each other, The rules for determining oxidation state are a little bit more complicated because we need to account for electronegativity differences now between the elements. And as a result of that, there are layers to the rules that, again, are a result of that electronegativity difference. So the first rule, and this actually is the same, that's true for formal charge as well, is that basically if we add up the oxidation numbers of the atoms in a molecular ion, we have to get to the overall charge, whether that be 0 for a neutral molecule or positive or negative for some kind of ion. Now, if we have an elemental form of an atom, we say that its oxidation number is 0. Now, elemental forms would be something as dinitrogen, dioxygen, dihydrogen, N2, O2, H2, halogens, right? Something like helium or neon, or not halogens, noble gases. Halogens would be diatoms. So, chlorine is Cl2, iodine is I2. Those would be elemental forms. For metals, it would just be the atom. It would be the metal, right? So sodium metal, Na, or copper metal, Cu. So any of those elemental forms would have an oxidation number of 0. Now, alkali metals, when they're in a compound, so in this case now they're not just a metal, they actually are part of a compound. Alkali metals are always +1. Alkaline earth metals are always +2. And that is, again, going to be a result of the electronegativity difference, because generally these metals would be bonded to a nonmetal in a salt, and there the nonmetal would be the more electronegative element. And the reason why alkalis are +1 and alkaline earth metals +2 is a result of their valence electrons. Alkali metals are group 1, alkaline earth metals group 2. So in many cases, we can use the valence electrons as a way to help us get to the oxidation state in most circumstances. Now, when we get into the nonmetals, or in general the P block of the periodic table, things get a little bit more involved because they don't always have a standard oxidation state. It is dependent on the molecule that we are looking at. So in general, nonmetals will have a negative oxidation number, again, because they tend to be the more electronegative elements on the periodic table. But we're going to see that there are some, excuse me, there are some layers to this. And we're going to start here looking a little bit into where the electronegativity comes in. So the sub-rule here, A, is that fluorine always is -1. Fluorine's the most electronegative element, and therefore it always is going to get the extra electron. So fluorine is always -1 in a compound. Now, the other halogens in compounds are usually -1, again, because of their relative electronegativity, but the exception is when they are combined with oxygen. And in this case, combined meaning that they are actually bonded directly to oxygen. In that case, and we'll actually look at a specific example of this in a couple of slides, in that case, they actually have positive oxidation states because there, oxygen is more electronegative. Again, we'll come back to that and look at an example in a couple of slides. All right, then we look at oxygen, a very common element in many compounds. Oxygen is usually -2, again, because of its electronegativity. The two exceptions being if it's combined with fluorine. So if you have an oxygen and a fluorine bonded, fluorine wins because it's more electronegative. The other exception is when it is in something called a peroxide. Peroxides are a special bonding motif because they are where you have an oxygen-oxygen single bond. And the most common one that we're familiar with is hydrogen peroxide, H2O2. Right? So in that case, we have a hydrogen singly bonded to an oxygen. That oxygen is singly bonded to another oxygen, which then is singly bonded to a hydrogen. So in that case, oxygen is said to be -1 because we have that oxygen-oxygen single bond. Now, for our purposes, hydrogen peroxide is really the main circumstance we would encounter if we were looking at a peroxide, but there are many other instances of that, especially in organic chemistry. But again, they're the two exceptions for oxygen. Otherwise, it's -2. Now, hydrogen basically can either be +1 or -1. It has one valence, so it can either lose the valence electron or gain one to get to a noble gas configuration. So oxygen is +1 if it's bonded to a nonmetal. It's -1 when bonded to a metal. Again, all based on the relative electronegativity difference is where that would be coming from. So most cases it's going to be +1 because we'll mainly be focusing on it with respect to nonmetals. Now, usually when it's bonded to a metal, we would call it a hydride. And again, that's where it would have the -1 oxidation state. All right, now let's actually use these in a couple of examples to show how we put them into practice. So we're going to start with pretty familiar molecule, ammonia. And in this case, right, ammonia, if we count up valence electrons to first figure out the formal charge in the Lewis structure as a way of comparing formal charge to oxidation state. So in this case, ammonia would have 8 valence electrons. When we go through and come up with that Lewis structure, we get this here, which is a nitrogen that has 3 single bonds and a lone pair, right? And in this structure, we have all 8 valence electrons represented. Now, in terms of formal charge, right, we have 2 different atoms, right? This was the way we said to calculate formal charge last week. We take the group valence, or the number of valence electrons, same thing, minus the number of line bonds, minus the number of electrons in lone pairs, right? So hydrogen is the same as water, so hydrogen would be 0. So these hydrogens all have a formal charge of 0. But for nitrogen, right, that is a group 5. It has 3 line bonds and 2 electrons in lone pairs. So in this case, nitrogen is also 0 formal charge, right? And here, if we add up, all zeros add up to 0, and ammonia is a neutral molecule. Again, because we need to make sure that the sum of formal charges adds up to the charge on the actual molecule or ion. Now, if we want to know the oxidation number of nitrogen or oxidation state of nitrogen, here's where we have to use our rules, because here nitrogen was not on our list. However, hydrogen was, right? So usually for oxidation number, we will have 1 or more elements that we can certainly place in terms of a value, and then the rest we have to figure out. So again, if we want to put this into some sort of formula, we can say the oxidation number of the element we're interested in this case nitrogen, would be the charge on the molecule minus the sum of known oxidation states. In this case, the known oxidation state would be for hydrogen, because here hydrogen's bonded to a nonmetal, it would be +1, right? So that means that the total charge from the hydrogens would be +3. It's a neutral molecule, so therefore nitrogen has to be -3. So charge on the molecule is 0 minus the sum of known oxidation states, which is +3, and that gets us to a -3 oxidation state for nitrogen. Again, overall ammonia is neutral, so the oxidation numbers also have to add up to be 0. All right, so here we have an ion, right? This is the sulfate ion, 2-, right? Again, 2 elements. Sulfur is not one that's on our list, but oxygen is. And in this case, oxygen is not bonded to fluorine. It's not in a peroxide. So we can immediately say that that's a -2 oxidation state. So we have that. The overall charge is -2. So therefore, our oxidation state of sulfur would be, again, charge on the molecule minus the known oxidation states. And that ends up being +6, because we have an overall charge of -2 minus 4 times a -2. That's coming from the oxidation state of oxygen. And there's 4 of them. So we end up with a +6. Now, if we wanted to look at the formal charge here, again, just to sort of see, relatively speaking, as comparison, what these values look like to each other, right? So we have an oxidation state of +6. Now, for a formal charge, we have to come up with a Lewis structure. Now, sulfate ion is one. If you look in many places, it would be drawn as this, where we have sulfur in the middle with 2 singly bonded oxygens and 2 doubly bonded oxygens. In this case, the oxygens with double bonds are formal charge 0, the sulfur is formal charge 0, and the singly bonded oxygens are -1, right? So -1 and -1 adds up to -2, and that's the charge on the ion. However, as I said last week, and we will get into more details on this in lab this week, is that hypervalency doesn't actually exist. And here around sulfur, we end up with 1, 2, 3, 4, 5, 6 bonds, which means 12 electrons, right? 6 bonds times 2 is 12. And in that case, we are certainly far beyond the octet. Now, as we'll see this week, a better way of describing this molecule in a Lewis structure is here on the right, because here we actually are obeying the octet rule. Now, what I've done to go from this left description to this right description is basically pull back the double bond, right? I've taken the double bond, or one of the bonds in the double bond, and pulled that back onto the oxygen. So what I'm left with here is 4 single bonds, which now puts 8 electrons around sulfur. I have now placed formal charges on all of the elements, but that's okay. Having formal charges on an element in a Lewis structure is completely fine, because again, the Lewis structure is only a model for the molecule, and formal charge is a formality. So going from 2 formal charges to 5 formal charges is not a problem. And in fact, it is better to have all formal charges than break the octet rule. So as far as I'm concerned, this structure on the right, or excuse me, the structure on the left is not correct because it breaks the octet rule. And ultimately, that is the most important thing that we need to follow when we are coming up with a Lewis structure. So this one on the right would be arguably the correct description, or the best description that we can come up with, obeying the octet rule. Now, for this, if you have questions of how I go from the left to the right, hopefully that will become more clear, because I will go over some examples during lab this week to help show what this looks like in practice. Now, just to sort of sum this up though, right, we said that the oxidation number on sulfur is +6. The formal charge now is +2 in this correct structure, right? So again, we can see these numbers are not the same, right? We're getting a different value for formal charge and a different value for oxidation state. We can also see, again, if we just compare these as 2 representations, even though this one I would not say is correct, this one is drawn as a formal charge of 0, right? So the formal charge here is going to change as a function of how we represent our Lewis structure. That's not the case for oxidation state, right? No matter how we count the oxidation state, it would always end up being +6. But the formal charge can vary a little bit. Again, if we were to draw something like this that would be historically called hypervalent. But as far as I'm concerned, the structure on the right is the preferable one. All right, now, just like last week, it's important to put context here as far as why we actually care about oxidation reduction reactions. So where exactly we use oxidation numbers, so for chemists, it's important in nomenclature, because in the names of molecules and compounds, we can use the oxidation state to indicate the specific compound we're looking at. Because here we have 2 iron chlorides, and the only difference is the oxidation state of iron, and therefore the number of chlorides needed to balance out the charge, right? So we would have iron 2 chloride and iron 3 chloride. Now, this is certainly, for chemists, this is important when we're trying to, look at different molecules. More broadly speaking, though, in terms of more application, would be redox reactions, because redox reactions are very critically important for many areas, especially energy. We will see in experiment 7, we're going to look at electrochemistry, which are redox reactions, and that is basically the chemistry that drives batteries, which are, again, very important as fuel sources. Also, biological systems. I'm going to go over an example briefly of a redox reaction that's quite critical for us in breathing, in terms of getting oxygen into the body. But it's only one of many examples where we have redox chemistry happening, in biological systems. So they are a rather important class of reaction for many different reasons. All right, so now that we have a little bit of background on what oxidation states are, now we can actually go through and define what oxidation is, what reduction is. So oxidation, to start, is the process of losing electrons. So in this case, this is where we are going to very readily apply our rules, because we're going to see in the course of a reaction that oxidation numbers are going to change going from reactants to products. And that is going to be the indicator that a redox reaction occurred. So oxidation states changing is the hallmark of a redox reaction. So oxidation is the loss of electrons. In that case, the oxidation states become more positive, going from reactants to products. Now, if something's losing electrons, that means something is gaining electrons, because electrons, just like matter, are not lost or gained in any way. They're always going to be conserved in terms of the total electrons that we are looking at. So the reduction part is going to be the gaining of electrons. So in that case, our oxidation state would get more negative, because it's gaining those negative charges. Now, important, just like precipitation reactions always had a precipitate and a supernatant, the same is true for redox reactions. These always happen together. You can't have oxidation without reduction, because again, the electrons that are lost need to go somewhere. They don't just exist arbitrarily in space. They have to go somewhere into another molecule. We'll also see that this is going to be true when we get to acid-base chemistry, that we're going to need an acid and a base when we're looking at this type of interaction. So again, now we will look at a couple of examples, again, to practice with the rules and also see what this looks like when we actually are looking at a reaction and trying to figure out where electrons are lost and where electrons are gained. So we'll start with this example, which is sodium metal, right? So this is Na solid, chlorine gas, Cl2, to form sodium chloride solid. Now in this case, again, these are elemental forms. Sodium metal is an element, chlorine gas is an element. So these two species would have zero oxidation state. That was our second rule. Now, if we look at the product, in this case, sodium, we know that's an alkali metal, it's +1, which means that chlorine has to be -1 because it's a neutral salt. So therefore, sodium +1, chlorine has to be -1. So if we now look to see how the oxidation states are changing, sodium is going from 0 to +1, right? That's getting more positive, so it's oxidation. It's losing electrons. Chlorine is going from 0 to -1. It's getting more negative, so therefore it's reduction. Now, if we look at the actual, again, electron bookkeeping, we have 2 moles of sodium, and each sodium loses 1 electron, right? It goes from 0 to +1, and that would be for 2 moles. So that would be 2 electrons. Now, in this case, chlorine, each chlorine here would be 0, and it's going to a -1. So again, we are gaining 2 electrons. So 0, and in this case, a total of -2 between the 2 chlorines. So 2 electrons lost, 2 electrons gained, right? The electrons balance out. We will actually come back again in experiment 7 because that electrons transferred is going to be important when we're looking at energy. And especially in the case of batteries, that transfer of electrons is going to be an important quantity that we will look at. All right, now we've already seen a redox reaction, well, a couple actually, but one here is in the chemistry of copper. In the final step, where we took our dissolved copper, that was the black copper oxide, we added acid to that, which gave us dissolved copper again, and then we put a piece of magnesium metal. That was the little silver chunk that we put into the tube. So in that case, what we did is we took copper ion, we added magnesium metal, and what we ended up with in the end was copper metal and soluble magnesium. Right, so in this case, we can see copper's going from 2 plus to 0, right, getting more negative, so therefore it's reduced. Magnesium is going from 0 to plus 2. It's getting more positive, and therefore it's oxidized. And again, gaining 2 electrons for copper ion, losing 2 electrons for magnesium metal, right? So again, we have 2 electrons gained, and those 2 electrons are the ones that are lost from magnesium. Now, there are 2 additional terms, right? We have oxidation, that's the process of losing electrons. We have reduction, that's the process of gaining electrons. Now, we have 2 additional terms, and that would be oxidizing agent and reducing agent. And here, if we consider, as I said, the copper ion is reduced, right? It's gaining 2 electrons. Now, we would call that the oxidizing agent. It is the agent that's causing the oxidation by gaining those 2 electrons, right? So the species reduced is the oxidizing agent. Alternatively, magnesium solid is oxidized, so that's the reducing agent. Again, it's the agent causing the other process. So copper ion is reduced, it's the oxidizing agent. Magnesium metal is oxidized, it's the reducing agent. It's causing the reduction or allowing the reduction to occur. Again, just 2 terms that you will hear somewhat often, so it's important to understand what they actually mean. All right, so if we look at another example, here we actually have the combustion of methane. So the first thing I'm going to do in this case, it isn't balanced. So I'm going to balance that. I end up with 1 mole of methane, 2 moles of dioxygen, 1 mole of CO2 gas, and 2 moles of gaseous water. Now, you may not have thought about combustion as an electron transfer or a redox reaction. So I will say electron transfer is another description for a redox reaction. So if you hear electron transfer or redox, we use them interchangeably. So in this case, thinking about combustion as a redox reaction is something you may not have done before. But we're going to go through and see how the electrons are changing going from reactants to products. All right, so if we look at the elements here, right, we have carbon, hydrogen, and oxygen. Only 3 elements, although in this case, the oxygen ends up in 2 different places, so we do need to consider that separately. So hydrogen, right, that's one of our rules, and in this case, it's bonded to carbon, which is a non-metal, so it's +1. So that means carbon here is -4. Oxygen, in this case, O2, is an element, so therefore it's 0. If we look at the products now, we have oxygen bonded to carbon and oxygen bonded to hydrogen. So in both of those molecules, the oxidation state would be -2 for oxygen because it's not bonded in either of the exceptions. So for water, we have -2 and we have +1 on the hydrogens. So that would be a total of +2 for the hydrogens, -2 for the oxygen. We get to 0. For CO2, again, oxygen is -2. So there's 2 of them, which would be -4. And then it's neutral. So that means carbon has to be +4. So what we can see then is that oxygen is going from 0 in dioxygen to -2 in both water and carbon dioxide, right? So it's being reduced. It's getting more negative, the oxidation state. So therefore, it is being reduced. Carbon, on the other hand, starts out as -4 and it ends as +4 in CO2. So there we are losing electrons. It's getting more positive and therefore it's oxidation. Right, now again, if we go through and count electrons, we can see there's only one carbon. So it goes from -4 to +4, which is 8. And here we have 4 oxygens that are 0, right? Because that's O2 and there's 2 moles of that. So in that case, there would be 4 oxygens. Again, 4 oxygens on the product side, each of those is -2, right? So here the oxygens are collectively gaining 8, right? So again, we lose 8 from carbon, the oxygens are gaining those 8, but it's not all in one atom, it's across 4 different atoms. All right, now just to give you, we'll come back to this in a couple of weeks to focus a little bit more on what we can see here is this iron center. But for right now, I just want to give you just a little bit of a heads up. It's probably something you've heard about before, but a very important redox process happens in us in hemoglobin. And hemoglobin is a metalloprotein that actually allows for binding oxygen and bringing that into the bloodstream. Now, all of that is going to happen at this iron center, and we'll again talk about that in experiment 6. But for right now, I just want to say that at that iron center, because the oxidation state of iron can change, it's going to allow for electron transfer. And again, in this case, that's going to cause redox reactions to happen as that O2 is bonded into the hemoglobin and eventually, reacted into the body. All right, now, our experiment this week is going to look at vitamin C in a tablet, in a vitamin tablet. And the reaction we're going to use to study this is a redox reaction. Now, our experiment is 3 main parts. First, we have to prepare a primary standard, and I'll talk about what that is. Then we need to prepare our samples, and then eventually we need to analyze the samples. Now, in this experiment, we are going to have multiple trials. Unlike last week, where we only had 1, we will have 3 trials in this experiment. And I want to start again, because the first part of this is making this primary standard. And we're going to be using a different type of device this week that we have not seen before, and that is pictured on the left. Right, so the device on the right is a graduated cylinder. That's something that we saw back in experiment 1 when we went to get the volume displacement for the zinc, right? We had the 100 mil graduated cylinder, we measured water, and then we added in the zinc electrode and got the final volume to get volume displacement of the solid. Right, and we saw in that experiment there were lots of lines. So this is actually a liter cylinder with same basic premise, right? We can see there's lots of tick marks, 100, 200, and then a whole bunch in between. 200, 300, and a whole bunch in between. Right, and we can also see that there are different levels, right? The tick marks have different lengths, right? At the 100, 200, they go all the way around. In the middle, the 250, 350, they're shorter, but they're longer than the remaining lines, which are in between. Right, so there are lots of different volume measurements we can make in a cylinder. Now, on the left here, this is something called a volumetric flask. And in this case, the first thing we notice, obviously it's a different shape, but visually we can see there are not many lines, right? In fact, there is only this one line here in the neck, right? So we basically have a bulb at the bottom and this long skinny neck. Right, and this line here is actually an engraved line. This is not, in this case, these are not engraved. These are just, based, I don't want to say drawn on, but they are basically like painted on with as they're manufactured for those volumes. This flask is actually engraved because a volumetric flask is a much more precise piece of glassware. It is calibrated to a much higher extent because this is the type of glassware we use when we are trying to make solutions with a known molarity or a known concentration more generally. And this is something we will use this week to make our primary standard. All right, now I will show in the video how to use this, but we're going to talk about in the next few slides how we actually go about making the solution. Because while it's not technically all that difficult, there are a couple of steps here that are not always intuitive when we start thinking about solution making. All right, first, to talk a little bit about a primary standard. So a primary standard is generally going to be a substance that is pretty pure, relatively high molar mass, and only slightly hygroscopic. Now, the term hygroscopic means the ability to attract and hold water molecules. And this is a property of some material, some solid materials, that when they are exposed to the atmosphere, the normal atmosphere that has water vapor, some of those materials actually will absorb water. Now, not every solid is hygroscopic, and some are much more than others. In this case, the practical implication of something being hygroscopic is that as we go to measure out the mass of a hygroscopic material, it is very difficult to accurately measure the mass because it's going to be absorbing water as we do that. And in this case, as it absorbs water, it's going to inflate the mass artificially. So say we want to measure out a gram. When we end up measuring that out, we don't know if that gram is actually all material or how much of it is water that's been absorbed. So for a primary standard, we want very low, for it to be very slightly hygroscopic, because in that case, we can be much more confident that what we're measuring out is only the material, and it's not picking up much water along the way. Now, that is going to translate because, again, being able to measure out exactly, again, if we want a gram, if we want 2 grams, whatever the number is, being able to accurately measure out that mass means that we will be able to get the exact amount of moles, right? Because 1 gram of whatever the compound is will equate to a precise amount of moles based on molar mass. Now, for our experiment this week, our primary standard is potassium iodate, KiO3. And we're going to see iodate is a polyatomic ion. They're not as common as, say, sulfate or carbonate, but they are an important class of polyatomic ions that are going to contain halogens and oxygen. So there actually are, for every halogen, there's a family of these halogen, oxygen, polyatomic ions. In this case, here we have IO3 minus 1. All right. Now, we're going to next talk about how we actually make a solution, how we go about making a solution, and then how we handle the error in that process. All right, now first, how do we actually use a volumetric flask? Well, I have this nice, I found this nice graphic that shows you visually the steps of what we need to do. Although I'm actually adding, the first step is not shown here because it doesn't actually involve an experiment, it involves a calculation. Because anytime we go to make a solution, we need to figure out how much material we need, right? A solution is going to have a solvent and a solute. So we need to figure out how much of each of those we need to make this solution. And anytime we are working with a solid solute, we need to calculate how many grams of that we need, right? As I said, that knowing the grams tells us how many moles end up in the solution. But we need to figure out how many grams we actually need based on our desired endpoint, or I should say our desired solution, right? Do we want a liter of 1 molar solution? Do we want a liter of 2 molar solution? Do we want 100 milliliters of 0.1 molar solution, right? We have to know going into the experiment what exactly we need. Now, once we have that set up, so meaning we know what we want, and we calculate how much material we need, then we can actually go and start making the solution. So first we weigh out the solid. Then we are going to take our volumetric flask, fill it about halfway with water. In this case, we always use deionized. Then we're going to carefully transfer the solid into the flask. In this case, you can see that's using a funnel to make sure that, this is a skinny neck. So using that funnel to actually get all of the solid transferred to make sure that we don't lose any of that solid, right? And now what's not shown here is the quantitative transfer part of actually rinsing the whey paper and rinsing the funnel to make sure that any residue is rinsed into the flask. Now, after that, once we've actually transferred all of the solid, then we need to actually dissolve the solid. Now, in this case, it's actually shown on a stir plate, although I personally prefer to manually agitate the flask because in that case, we don't need a stir bar. So you can see here, here's the stir plate, and this little, looks like a white vitamin on the bottom, or a gray vitamin, is a stir bar, right? This is basically a magnet, and the stir plate is able to control that magnet to spin in order to actually agitate the solution and dissolve the solute. In this case, though, if you put in a stir bar, you have to then take it out and make sure that you don't lose any drops of solution. So it's just an extra step that I don't find necessarily useful. So manually agitating the flask is what I will do in the video because I think it's just easier. Now, once the solute's fully dissolved, then you go in and you add water up until you hit the engraved line. So you can see it's a little hard to see, but they do indicate there's this little thin line there. It's a little bit more visible here, and then also a little less visible there, and then eventually the meniscus is on that line, right? So that line is the volume reading. So then what we end up with is a mass of the solid and a volume of solution, right? So those would be the two data points we would record. There are lots of steps in between those, but in terms of calculating something, we have a measured mass and a measured volume. All right, so now let's actually try to make a solution in this problem. So here we have a student who needs about 200 milliliters of 0.75 molar copper sulfate pentahydrate, which has a molar mass of 249.68 grams per mole. Now, in this case, even though we need 200 milliliters for the experiment, the only thing we have is a 250 ml volumetric flask. Now, as I said a few minutes ago, the volumetric flask can only measure that total volume. So even though we only need 200, we have to make 250. And in general, we would always make a little bit extra when we are preparing a solution. Because if we needed 200 and made 200, there'd be very little room for any sort of issues that may come up, whether that just be an accident or maybe we realize, oh, we need to run an extra trial, right? So generally, we would try to make extra solution as a good practice. Again, just better to be safe than sorry and have that ready. And again, we'd only be making about 50 milliliters extra in this case. It's not a ton of volume. Then we also have a digital balance. Again, same supplies in terms of the measuring devices. We have the balance, we have the volumetric flask. All right, so as I said, the first thing we need to do is figure out how much salt we need. Now, I think probably the hardest aspect of this is that this initial calculation is a preparatory calculation. There are no sig figs at this point because these are just numbers, right? We're saying we want about 0.75 molar copper sulfate, and we know that our final volume is going to be 250, right? But these are not actually measurements yet. Those are just numbers. Now, once I have my calculation completed, which I'll do on the next slide, then we can actually go in and measure the mass of the salt. Eventually, then we will, we'll do the same process on the previous slide, and eventually we'll end up with a final volume of solution, which is going to be the volumetric flask with error. Right, so that's where, when those measurements are made, that is where the error and sig figs will come in. Not in that initial calculation, but in those actual measurements. All right, now, even though we're basically working backwards again, what we always need to do is take our measured values, again, because they will now have sig figs and error, and we actually need to calculate the exact actual molarity using those measured values. Now, it should basically be 0.75 molar because that's what we were hoping to make. But is it just 0.75? Is it 0.750? Is it 0.7500? That's where we don't know until we actually have these measured values and calculate it. All right, so now what does this look like in terms of actually solving for this information? Well, again, the first thing we need to do is our preparatory calculation. When I first learned about this, my teacher called these a back of the envelope calculation, right? It's just, you just jot this down on a piece of scrap paper and figure out what you actually need to measure out in making this solution. So the way I do that is to take total volume. Again, that would be 250 milliliters from the flask, because even though I only want 200, I have to measure out 250. My desired molarity is 0.75 moles per liter, right? Volume times molarity is moles. Then to get to grams, I take moles times molar mass, which I gave on the previous slide. So what I get out from the calculator is 46.815 grams. Right now, I just reported this. It just so happens that the numbers I picked gave me 3 decimal places. But this is the exact number. So if there was any more decimals, I would have listed them here, because that's just a number from the calculator. There's no significance to this yet. Now, then now I know, okay, I need 250 milliliters of solution. I need to measure out 46.815 grams of solute. So now I go into the lab and run my experiment. Or in this case, I make my solution rather for an experiment. So I go in and I measure out the salt. That would be 46.815 plus or minus 0.001. Right, now for the sake of this calculation, I'm using the exact number. But that being said, if I had a slightly different number, so for example, maybe I couldn't get to exactly 46.815. Maybe I ended up at 46.816 or 817. Right, that's okay. Even though it's a little bit higher, that's fine because I know exactly the number that I recorded. Right, especially with some salts, they may be in sort of large chunks that can't actually be broken up all the way. So getting to exactly this number may not be feasible. Again, for the sake of the problem, I just took the exact number. But as you'll see in the experiment this week, when I actually did the solution making, I had a little bit more than what I had originally intended. But again, it doesn't matter because I knew the mass that I'm actually measured on the balance. And again, this number just comes from my volumetric flask. Right, now you can see here, if we think back to experiment 1, right, 100 mil graduated cylinder had an error of 0.4. And a 10 mil graduated cylinder has an error of 0.1. In this case now, we can measure 250 milliliters, and that also has an error of 0.1. Right, so the difference between the absolute errors is pretty significant, because here I can get 250 milliliters with only an error of 0.1. And on a graduated cylinder, I would get far less volume, or in this case, if I did get this much volume, I'd have a much bigger error. I don't know off the top of my head what a 250 milliliter graduated cylinder error would be, but certainly bigger than 0.4 because that's the error on a 100 mil cylinder. All right, so now I have my two measurements. I've made my solution. My last step is to actually calculate the exact molarity. So now I basically, this is my original calculation. I'm basically working backwards, but now I'm actually using sig figs and error, right? So I take my grams with error, convert to moles by molar mass, and then I divide by volume. In this case now, this volume does have sig figs and error because that volume is now a measurement from the volumetric flask. Now, notice what I've done here, right? I've taken 250.0 divided by 1,000. That gets me 0.2500. I've also needed to scale my error because 0.1 is an error in milliliters, but I'm converting my volume to liters. So I also need to divide 0.1 by 1,000. So that's where I'm getting this error of plus or minus 0.0001. That is 0.1 over 1,000. Because I must scale my error to the same unit as my volume. All right, so in this case, I go through. My mass is 5 sig figs. My molar mass is a constant. That doesn't impact sig figs. My volume is 4 sig figs, right? So now my molarity goes to 0.7500. So that is my 4 sig figs. Now be aware, right? The calculator is only going to spit out 0.75. The calculator doesn't take into account the sig figs you type in. It just gives out the number. So the calculator would spit out 0.75, but again, you would have to report this with 2 zeros at the end because of the 4 sig figs in the volume. So again, another just small detail that's important when you're actually calculating these. All right, in terms of the error, this is actually basically the same thing as density. I have division, and I have two errors, an error in the mass, an error in the volume. So basically what I have here is, here's my relative error in the mass, 0.001 over 46.815. Here is my relative error in the volume. Now what I've done here, because I don't want to write out all those decimals, is I just show the fraction in milliliters. Because 0.1 over 250 is exactly the same as 0.0001 over 0.25. It's just that I don't want to have to write out all the decimal places, so I express the fraction still in milliliters. Now, again, in this case, there is no error contribution from the molar mass, right? Unlike last week where we had just that one error value, here we now have two. So basically that molar mass we don't have to worry about with respect to the error. It's already been accounted for in the value. So we basically just have these two fractions, add them together and multiply by the final value, which is the 0.7500 molar. That gives us this unrounded error, which we round to 1 sig fig, which gets us to the 0.0003 molar. And then lastly, right, so now this is 4 sig figs, which is good. This is 1 sig fig, which is good. Now I pair these two numbers together, and both of them are 4 decimals, right? So this is an example where they match without having to do anything extra. All right, now we will come back to this in lab because I want to take some time during lab this week to go over this again and make sure that everybody understands how to do this, because this is basically the first calculation of the lab report. Pretty much exactly what I've done here, just with the data from the module. All right, last thing here, I did do this in one step, right? I took grams to moles over volume to get right to molarity. I did not do this in 2 steps and get an intermediate error. There's nothing wrong doing it that way, but it's important if you do it that way that you use the unrounded numbers. So in order to basically circumvent that altogether, I just do it in 1 step, and then I do my error at 1 step in the end, right? I combine both of these errors in my final error calculation. All right, now in terms of our experiment, we are going to be looking at, again, the vitamin C content in a vitamin C tablet. And we are going to be using our primary standard, the potassium iodate, KiO3, in a titration. So this is going to be the first of several times where we actually do a titration. We also will be able to practice and set up a titration apparatus in the at-home experiments, given the contents of the kit. And a titration is pretty much going to use a device called a burette. A burette is basically a very big pipette, but it is a bit more precise, and it's also much larger because burette holds 50 milliliters of solution, and it's going to have a much easier, instead of you having to use a bulb like we did with the pipette, it's going to have a valve on the bottom that will allow us to control the flow of solution. So that will be in the video. I will demo what that looks like in terms of cleaning that, setting that up, and preparing it. But we are going to be using the burette to actually dispense the primary standard into our reaction flask. Now, the reaction flask is going to contain a whole bunch of different things, and they are going to be involved in two separate reactions. The first of which is Barron equation 30.2, and that is as follows. So this is, be aware, a net ionic reaction. This is not including everything in solution. The spectators are not presented here. Because potassium iodate, right, that's our primary standard, but it's the iodate ion. Since that's a soluble salt, the iodate ion is what's reacting here. The potassium ion is not. That is just balancing charge. So what's happening here is the reaction of iodate, IO3 minus, with iodide, I minus, in the presence of acid, H plus. This is a proton, but this proton, H plus, is coming from sulfuric acid. Now, what we are going to form, Barron calls the triiodide ion, I3 minus 1. However, there is a better way to describe this, and we will see why this is better in a moment when we look at oxidation states. And then we produce water. Now, in terms of oxidation states, right, if I'm saying this is a redox reaction, it's important for us to go through and actually figure out what's happening with respect to oxidation numbers. So if we look at this, again, this is an example where iodine, a halogen, is bonded to oxygen. So this is a case where oxygen takes priority and it gets -2, right? So in that case, there are 3 of them. That's -6 with a -1 left over, which means this I is +5, right? So that's why I say here, iodine is +5 in iodate. Now, I realize that we have iodate, iodide, and iodine, which is the element. So just, please keep track of that. All of them sound quite similar, just a few letters different, but they do mean something rather different in chemically in terms of what they are. Now, the other two, iodide ion, that's simple because it's just -1. It's just a single ion, so we already know the oxidation state. Same goes for H plus. Now, if we look at the product side, this is where viewing it the way I described it here is I2.I minus is better. Because if we have I3 minus 1, then that means we have a -1 charge split over 3 I's, right? So that would mean that it's a -1/3 per iodine, right? But we can't really split an electron into thirds. If we get a fractional oxidation state, that really is an average value. So, just saying that -1/3 iodines would be the average oxidation state, not the actual oxidation state. Well, it turns out I3 minus is actually this molecule here, which is elemental iodine, I2, with this dot, right? So this is similar to the dot I used for a hydrate, But in this case, this is not a solid, this is an aqueous. So here I'm using the dot to basically be a representation to show that this I minus is stuck to the I2. It's something that we call an adduct, and I have that word on the next slide. It's ADDUCT. And an adduct is basically here, in this case, we have this I minus, this iodide ion stuck to an elemental iodine. And that's where we get the I3 minus 1. Now, in this case, it makes the oxidation states more clear because elemental iodine is 0, iodide ion is minus 1, right? So the minus 1 is actually only on one of the iodines. So what we have here is this I is going from plus 5 to 0, and some of these I's are going from minus 1 to 0, right? So we have the same element, although it's coming from two different places, some from iodate ion, some from iodide ion. So the same element is being both reduced and oxidized, just depending on the source. So this I in iodate is gaining electrons to get to 0. It's being reduced. I minus is losing electrons to become I2. So in this case, these are our reduction and our oxidation. Here we have reduction of the iodate, the I and iodate ion to get to I2. And here we have oxidation of I minus to get to I2. All right, now this reaction, basically everything's going to be in the flask, I minus and H plus. And we are going to be adding in the KiO3 by the burette. So that's what we would call, the titrating part would be dispensing the primary standard into our reaction flask. So this reaction we actually control because we're the user is the one who's going to dispense in the actual titrant or primary standard in this case. Now, as we do that, this product is going to form, this triiodide. And then what I'm going to do is the next reaction is going to occur, which is with the vitamin C. So this is Baron 30.3. And here now we have the reaction of triiodide with the vitamin C. So this is vitamin C, triiodide, and water because we're in aqueous solution to make this molecule here remake I minus and remake H plus, right? So these were remaking some of the reactants from 30.2. Now, in this particular reaction, because this is a carbon-based molecule, this is a little bit more difficult to understand the redox part based on what we've talked about so far. But what we can do is infer what's happening based on logic. Because if we look here, we can see this one is more simple to see because we have I2, which is elemental, becoming I minus, right? So that means that the iodine is gaining electrons. Now, if something's gaining electrons, that means something is losing electrons. And here, the only thing that can really lose electrons is vitamin C. If water lost electrons, we would form O2 gas because hydrogen is already +1. It has no more electrons to lose. Oxygen is -2. It could lose electrons, but we'd have to form O2 gas. And since O2 gas is not formed, we know that water is basically not changing. So what's happening here is the vitamin C is losing electrons. Now, when it comes time to organic molecules, oxidation numbers don't really work the same way because we are looking at only a handful of elements and the bonding motifs are going to change a lot. So what we have to do there is look at the electron density around the elements. Now that's something that you'll learn when you get to organic chemistry, but that's just a small taste of what that looks like when you get to organic. So for our purposes, we're just going to say that vitamin C is oxidized, and exactly how is not going to really matter too much right now because it's beyond what we can get into given everything else. But as a result of the I2 gaining electrons, we know something has to lose electrons, and that species has to be the vitamin C. Now, this reaction is being controlled by 30.2 because 30.2 is what's going to produce triiodide, and that is going to then react immediately with vitamin C. Now, it turns out, and you can go through and check this yourself if you want, but the vitamin C is the limiting reactant, right? We do have two reactions that are happening here, but based on how we've measured all of our compounds out, vitamin C is limiting. So that means that equation 30.3 is the limiting step of these two reactions. And what's going to happen is that as soon as vitamin C is fully consumed, meaning that it goes to zero, right, this reaction can no longer happen. But the previous reaction can happen, right, 30.2. Which means that we can still produce triiodide in solution. Now, the reason that that's going to be important is that once equation 30.3 is done and can't happen anymore, when we add just a little bit of excess of potassium iodate to make an excess of triiodide, what's going to happen is that that triiodide can react with our indicator, which is starch in this case. So starch is something we also add to our reaction flask, but it doesn't actually react or do anything until the very end. Because the only way that that will actually do something is when you have triiodide in solution not being consumed by something else. Because we form this triiodide starch complex, which is not super strong in the sense that if triiodide can react with something else to become more stable, it will. Now, once vitamin C is consumed all the way, triiodide and starch can react because there's nothing else that either of them can do individually. Now, the importance of this complex is that there's going to be a very visible color change. The reaction mixture is going to be pretty much colorless the entire time. Everything that we add in the beginning is basically colorless, whether it be a white solid, the titrant is going to be colorless. And as soon as we hit this, what we call the end point is when we have now caused this color change to occur. And again, that will be easy to observe. And that color change is going to be the indicator that our reaction is done, in this case 30.3, and we will now know the volume it took to reach that point. Now that's important because if we know the volume it took to reach that point, we can calculate how much vitamin C was present as a result of that volume. Now, I'll come to that in a moment in terms of what we actually do with those numbers, but just to sum this up, so we are titrating in potassium iodate, which is going to generate triiodide in solution in our flask. The ascorbic acid that's in our flask is going to react with triiodide until it's totally consumed. And once that has occurred, the excess triiodide that we form in solution can react with the starch to make that dark blue-black color in solution, which again is the point at which we're going to say, okay, the reaction is over, and that is my endpoint volume. Now, in terms of the data and analysis, and this is something also that we can talk about in lab this week, since these calculations are a bit more involved than we've seen so far, since this is our now third experiment. So in terms of the data, we are going to have the mass of the total tablet. And important, a vitamin C tablet is not pure vitamin C. There are always binders and different types of preservatives that are present to keep the tablet together and to keep it fresh. And for example, if it's kids' tablets, they may put sugar in and food dye and things to make it look more appealing and taste better, right? But basically, vitamins are not going to be pure, whatever the vitamin supplement is, in this case, vitamin C. Now, we're also going to know, so we have a total tablet. We are going to split that tablet into samples. And as I said, there'll be 3 samples. So we're going to have the mass of each vitamin sample analyzed. And if the tablet isn't pure vitamin C, then the sample isn't pure vitamin C. So we're going to be able to figure out in that sample how much of it was actually vitamin C itself. Now, the other piece we will know is the volume of potassium iodate per trial. And as I said, the volume of potassium iodate dispensed per trial is going to be the point at which that color change occurs. And we will also know the exact molarity of the KiO3 based on the solution that we made. So if we know the molarity and we know the volume of KiO3, then we know something very powerful, which is the moles of KiO3. Because molarity times volume is moles. And once we get to moles, we know the 2 balanced equations that Barron gave us, 30.2 and 30.3. So therefore, if we know the moles of KiO3, we can figure out moles of anything else based on whatever we want. In this case in particular, it would be moles of vitamin C. But again, we now have moles of something, we can relate it to anything else. All right, now for some safety considerations, as usual, wearing PPE, all the necessary PPE, understanding the waste disposal in terms of what goes where, and making sure that nothing goes down the drain other than just plain water. There's going to be a lot, as you'll see in the module, there's a lot of solids being measured. So just like last week, trying to minimize scatter with those, that we don't contaminate things. We're not, spilling that solid around or breathing that in. We are going to be using sulfuric acid. So we do need to be careful when using that, even though it is rather dilute. In terms of equipment, we're going to be using a burette, which is a long glass tube. So it's important to just take caution with that. And one small note is when we are filling the burette, we would use a funnel to actually get the solution inside of the burette, but we would never want to leave the funnel in the burette because it would make it top heavy and more likely to fall. So that's a particular safety concern with the burettes. And then lastly is organization. Because we're using multiple reagents and we have multiple trials, keeping everything neat and organized is important so we don't accidentally add the same reagent twice and then accidentally not have all of the necessary compounds present in our reaction mixtures. All right, so I'll just leave you briefly. I wanted to say just a few words about starch in terms of explaining where that color change is coming from. So starch is an organic compound composed of amylose and amylopectin. And it turns out that amylose is a long polymer chain of glucose units, right? Glucose is a sugar. And it's a long chain of these glucose units connected in a particular way, what's called an alpha acetal linker. The connection itself isn't important, but it happens to be the particular type of connectivity. Now, as a result of those connections, the amylose can coil. It causes it to form spirals. You can think of it as a slinky, right? And now, also as a result of the structure, the amylose coil happens to be of the right diameter for the triiodide to fit inside of it, right? So you can see here, right, this is the gray ribbon is the starch coil, and these 3 circles inside of it are the triiodide ion. Same thing here. This is looking down, sort of down the tube or down the coil, right? And these 3 purplish spheres are the triiodide ion. Now, as a result of that triiodide going inside the spiral, the coil, that's where that color change is going to come from. There's going to be a disruption of the electrons and rearrangement as those triiodide ions go inside the starch coil, and that's where that color change comes from. Now, also, just to little bit about vitamin C, right? It's something that we probably have all heard about at some point. We know it's rather important that we get enough of it to stay healthy. And that's due to the fact that we actually lack a particular enzyme that makes vitamin C. So some creatures actually have this. It's called L-galonolactone oxidase. And that's an enzyme that actually would produce vitamin C in living organisms. But we don't have this enzyme, which is why we have to get it through our diet. Now, vitamin C has a lot of biological importance, but I think one of the more important ones is that it is needed in many enzymatic reactions. So at this point, I didn't talk yet about what an enzyme is, but enzymes are very important in biological processes, or biochemical processes rather, and one of them happens to be collagen synthesis, right? So, growing up, you may have heard about scurvy, right? Back in the older days when people were out to sea for long periods of time, they would end up getting scurvy if they didn't have enough vitamin C in their diet. And this is because the synthesis of collagen, which is a very important connective tissue in us, wasn't happening. Now, I mention this because we're actually going to have collagen fibro growth as part of the Excel activity that we'll talk about soon. So I just wanted to mention that in terms of, again, where this collagen is coming from and its relevance in terms of being an important compound in us. All right, so then I will leave you with announcements as usual. So the quiz this week will be released on Tuesday, again, because of the long weekend. The quiz is pushed back one day, so it will be released Tuesday at 5 p.m. and then close Wednesday at 1 p.m. Now, Dry Lab 2A is assigned this week. Just like Dry Lab 3, it will be, you'll have it for 2 weeks, or rather you have 2 weeks to submit it. It's due on June 14th. And Dry Lab 2A is going to cover oxidation states. So you can refer back to slide number 3 from this lecture. There's nothing additionally that I have to present on Dry Lab 2A. It's going to just be practice utilizing those oxidation states. Now, for next Monday, June 7th, as usual, we're back to a normal schedule. Pre-lab for experiment 3 on lab archives, including all data and observations and all the other relevant 4 parts. Submitted to Courseworks. Again, this is also a notebook discussion, so same as experiment 1 and experiment 2. Handwritten calculations is described in the notes. I will remind you, again, since there are 3 trials, you only have to show sample calculations for 1 trial, and then you can report the answers for the other 2. So, show, for example, write out calculations for trial 1, and then you report the answers for trial 2 and trial 3 on the report sheet. You don't have to write those out in triplicate, only 1 set of sample calculations for 1 trial. 2 report sheets found on Courseworks. This is an internal report sheet. Again, you can, as usual, use that to craft your data table. Although I will say there actually is a decent amount of data this week that we don't calculate with, because the mass of potassium iodide, the mass of sodium bicarbonate don't actually come into calculations, but they are data recordings that I take in the module. And then lastly, again, will be the notebook discussion. 3 questions as usual for that, and that's found on the Coursework site in the module. And then for June 7th, also Dry Lab 3. But Dry Lab 3 is something we'll talk about again in lab this week. So in addition to experiment 3, I'm going to talk more about Dry Lab 3. And then next week, we'll be back to a normal routine. Quiz 3 on Monday. We'll talk about experiment 4. And then we're going to start talking about the Excel activity because graphing is going to be quite important in the experiment 4 lab report. All right, now please save any of your questions for lab this week, or feel free to post them to the discussion board in the meantime. So if you watch this at some point before your lab period, which I hope you do, please feel free to post questions to the discussion board or save them for class, and we can chat at the beginning when I talk a little bit about this.